Okay, well, why don't we go ahead and get started? There may be a few others joining us, but we'll go ahead and get started. And again, welcome to today's IWCS webinar. My name is Dave Cadu, and I'm honored to be the CEO of IWCS, and I will be your moderator for today's event. Just a few housekeeping items. As always, as an attendee, you're part of a larger audience. So during the presentation, all participants will be in listen-only mode. And also as a reminder, this event is being recorded for rebroadcast. It will be posted as are all of the webinars that we have produced on our website at iwcs.org. And at the end of the presentation, you'll see the contact points, the email address for Earl, in case you wish to contact him after the event. We encourage you to submit written questions at any time during the presentation using the chat panel on the right of your screen, or if you open up the chat, you can type in your questions in the space at the bottom and be sure to hit the send button, and your questions will be addressed time permitting at the end of the presentation. So again, type in any questions you have during the presentation. Our IWCS webinar series event is hosted by the Cable and Connectivity Industry Forum. Today we welcome Dr. Earl Parsons. He's the Director of Data Center Architecture Evolution for CommScope, located in Texas in the USA. Earl will be presenting his paper on the optical transceivers and structured cabling with expanded beam connectors as an alternative to active optical cables. Dr. Parsons is the director, again, of data center architecture at CommScope. He joined CommScope in 2014 as a principal optical engineer. Prior to joining CommScope, Earl received his Master's in Science and PhD in Optical Sciences from the University of Arizona, and was a senior member of the technical staff for TE Subcom, formerly known as Tyco Telecommunications. Dr. Parsons also served as an editor of the IEEE 802.3 DB 2022 standard. His interests include multimode and single mode fiber optic systems to enable artificial intelligence data centers. Clearly a very active part of our industry right now. So we very much appreciate Earl presenting his paper today. And again, please feel free to enter any questions in the chat. So Earl, thank you.
Thank you, Dave. I also want to thank IWCS for this opportunity to present. Thank everyone joining the webinar, either live or watching it on demand. And I especially want to thank my co-authors. I have Cam Patel, who works with me at CommScope, Rich Baca, who when we did this test was at Microsoft Azure, and Kevin Chalupka and Paul LeBlanc, who are with 3M. So we're seeing changes in the data center architecture. Not surprising, this industry has been one of constant change. But the biggest change in data center architectures that I'm seeing in the near term is happening in the data hall, where we have the servers that do the work and generate revenue for cloud and hyperscale companies. So in a traditional data center architecture, at least what we've seen the last few years, we have something similar to what we see in the top left of this image. We have a rack full of servers, and each server is connected to a top of rack switch called a TOR. And this connection is done with copper cables. It's short, maybe a couple of meters. And then from the TOR, we connect to what are labeled here as tier 1 switches with the fiber cable. Some people call these tier 1 switches the leaf switches. So everything from the TORs, the tier 1s, and then up to the spine switches and the higher levels, those are fiber connections, those have been around for a while, and I don't see a lot of changes there. But the big changes is happening here, what we see in this image. So here's a concept. This has been presented a few places by people who work for Microsoft, where instead of having a TOR, we eliminate the TOR, we replace it with a patch panel, and then we connect each server to the tier 1 switch. And that could be in the middle of a row or an end of row. Now, the distance between the server and the tier 1 switch is too long for a copper cable, so these are done with fiber connectors. A good example of this TOR elimination concept is these superpods that NVIDIA talks about. This is an image from NVIDIA's site. They are involved with something called artificial intelligence, or AI. You probably heard a little bit about that recently. And what they have here is they have these beige boxes are GPU servers. Each of these have 8 GPUs, which are the units that do computation for artificial intelligence and machine learning. And these racks do not have a top of rack switch. Instead, there's only 4 servers in each rack, and they are connected to the first tier switches here in the middle of the row. So again, going from one rack to another to get to the first level of switching, that's too long for copper cables, especially if you're looking at 50G and 100G lanes or even faster. So we need to go with a fiber connectivity between these GPU servers and the first level switching. We also have quite a bit of memory in this SuperPod that also needs to be connected to each of these servers with a fiber cable. So we have a minimum distance. We got to go from one rack to another in the row to get to the switch. But we also have a maximum distance. You want to keep these GPU clusters small. You want to keep the servers and the switches close together because the applications that are running are very sensitive to latency. If you have really long links, it's going to take longer from the data to get to one point to the other. It's going to take a lot longer for your computation to be done. And with these AI clusters, people want to use them, and they want to use them efficiently and fast because they are expensive. Typically, the longest links we'll see in these AI clusters between the servers and the switches is 100 meters. So multimode fiber is an obvious solution for these applications. Again, it's too long for copper, and it's so short that we don't get the big benefit from single mode fiber. For single mode, you need to, single mode can help you get beyond 100 meters, but we're limited to 100 meters here, so multimode's a good case, especially since the optical transceivers for multimode are about half the cost as single mode, and they each use about 1 to 2 watts less power when you use multimode. So if we want to connect these servers directly to the switch with fibers, there's some concerns about what the fiber connectivity, how that's going to be handled. Now, as we know, you have to be very careful with fiber connectors because they have to be clean, they have to be properly polished, they have to be well maintained to get good performance. And if the end faces of these connectors are contaminated, that can introduce loss, it can cause problems that will affect the whole cluster. And there's some concerns about the people working in these data halls. If they're not experienced with fiber connectivity, they may not properly care for the connectors, meaning the end faces will get contaminated and it'll cause problems with fiber connectivity. So one solution that we've seen several deployers of these AI clusters use is something called an active optical cable. So an active optical cable is basically you take 2 optical transceivers and they are prepackaged together with a fiber cable in between them that connects them. So in this study, we investigate using expanded beam connectors with fiber cables to replace these AOCs. So there are some advantages to using structured cabling and transceivers instead of active optical cables. The first one is it's a lot faster to deploy because you can separate when the passive cable infrastructure is deployed versus when the active equipment is deployed. Also, when you upgrade your system, from one speed to another. If you use AOCs, you have to remove all those and repopulate your cable trays with new AOCs with a faster data rate. If you have passive cabling, that can remain and support several generations of transceiver speeds. The speed of deployment is very important for these AI clusters. Again, they cost a lot of money. To get that return on the investment, you need to have them up and running fast and be used very efficiently. With expanded beam connectors, we take the light from the fiber and increase the size of it when it gets to the connector end face. That makes the signal more robust to contaminants, because a contaminant of a certain size will have less of an impact on the total signal because it's blocking a smaller portion of the beam. So with these expanded beam connectors, we don't have to clean the end face when we're mating or demating or doing any changes with the connectors. So these connectors are easier to install and much lower risk of having something going wrong when they're installed. Here are a couple pictures from my co-authors from 3M of these expanded beam connectors. These particular ones have a 12 fiber ferrule. So we have a 12 fiber ribbon coming in. There is a prism with some lensing on it that takes the light from the fiber, turns it 90 degrees, collimates it before it gets to the end face. And on the end face, we also have an anti-reflection coating. So we have good return loss for these connectors. They mate, they slide together. There's no external springs. They use the spring force from the fibers themselves to ensure that these connectors stay mated together. And like I said before, the spot size is a lot larger, so any contaminants you have will have less of an impact on the signal, to the point where we don't need to even clean these connectors when we're installing them. To test the overall system performance of these connectors and to make sure they wouldn't do anything to degrade or disrupt the optical transmission, we did a series of experiments. We started with some AOCs. These were 200G SR4, and now each of these have 4 50G PAM4 lanes. So each side has 4 transmit and 4 receive, total of 8 fibers. These AOCs would report through the Ethernet tester we used the received power of each lane, and we would measure the BER, the bit error ratio, for a 2-minute window to measure the performance. Now I took the BER and I converted it to a value called Q, and you can see the math for BER versus Q down below. And we did that because it's easier to talk in terms of margin with Q as opposed to BER. Some of the results I'll report will be over 9 dB of Q, so 9.15. That corresponds to a BER of 1E minus 16. And when you see that value in the following slides, that means in the 2-minute window I was measuring the BER, I didn't see any errors, prefect errors. Like I said before, throughout all these tests, the EBO connectors were not cleaned before mating. Let's see, for these 200G SR4 transceivers or AOCs, they have specifications defined by IEEE Ethernet standards. The receive power has to be more than minus 8.4 dBm, and the BER prefect has to be below 2.4 e to the minus 4. This ensures that the FEC, the forward error correction, will correct all the errors and will have an error-free link end to end. So that BER corresponds to having a Q greater than 5.43 dB. So important thing, a low BER is good and a high Q is also good. So we'll show a lot of different experiments, a lot of results, but the bottom line is with a 150 meter reach with 2 EBO connections in the path, all the tests we did, we had at least 7 dB of power margin and at least 1.5 dB of Q margin. So it's going to be very good results and show that these expanded beam connectors, these EBOs, are well suited to these short reach applications. So here's the first experimental setup that we had. I had 2 Ethernet testers. Each one had one end of this 200G SR4 AOC. They were 3 meters long. And for this test, this would be like if we had this Ethernet tester and AOC, this could represent the GPU server in one rack, and this Ethernet tester and AOC and would be the first switch in another rack in the same row. Each AOC would transmit 4 50G lanes, so we had 8 fibers used in total. And I would record the BER and the received power for each of this lane. And this experiment is our baseline. So we don't have any connections in the path. We just take the 2 ends of the AOCs, plug them in, measure the BER and the received power. And here are the results for our baseline. This is Q versus received power for each of the 8 AOCs that we measured. And again, each AOC has 8 values to report, 4 lanes in each direction. And the black dash right here, this is our specification from Ethernet standards. So we have to have more than minus 8.4 dBm for received power and a Q higher than 5.4 dB. And all the results are well above that. We've got quite a bit of margin with these transceivers, these AOCs. And again, these values above 9 dB of Q mean that we didn't have any errors in the 2-minute window. So here's the second experimental setup. What we did, we took those same AOCs, we cut them in half and terminated them with these expanded beam connectors. Then took different cables of OM4 of different lengths, put EBO connectors on the end of those as well, put them in between, and would measure the results for different lengths. So with this scenario, this Ethernet tester again could represent the GPU server in one rack, and then this EBO connection could be at a patch panel at the top of the rack. Then we'd have this cable running from one rack to another patch panel, and then we have a cable from the patch panel to the AOC in the switch. We tested 4 different lengths of OM4. We had one that was less than a meter, 50 meters, 100, and 150. So again, with these AI clusters, the maximum limit we'd see would be about 100 meters. We want to go a little bit further to try to stress the system. So some of these results will talk about matched AOCs and unmatched. The matched were the ones that originally came prepackaged together, and then the unmatched was where we took different combinations. And all of these results in the next couple slides will have 2 of these expanded beam connections in the path. All right, so here's the first set of results. I have Q versus link length for 3 of the AOCs of the 6 that we tested this way. There are 8 lanes per chart. And then on all of these, the leftmost data point for 3 meters is the uncut AOC. So that's our baseline. So we have the uncut AOC. Then we have the cut AOCs with 2 EBO connections in the path with a short patch cord between, a 50-meter spool, 100 and 150-meter spool between. So these are really encouraging results because our Q limit is down here, this black line. So we have quite a bit of margin, even if we go out to 150 meters, which is longer than we need to go. Even if we have 2 these expanded beam connections in the path, everything's working really well. And here are the same tests with 3 other AOCs. So we tested 6 in total this way. Okay. Next, we have the same results, but for unmatched transceivers. So with this graph, I took AOC 1A in one port and AOC 2B. These originally didn't come packaged together, but wanted to make sure that things would work even with unmatched transceivers. And again, whether we go have a short patch cord of 3 meters total or 150 meters, we still have quite a bit of margin compared to our Q limit. And these are 3 other combinations that we tested. So since that worked so well, we decided to push it a little bit further. So for the third experimental setup, we would concatenate these spools together. So we had 200 meters with 4 expanded beam connections in the path, 250 also with 4, and then finally 300 meters with 6 expanded beam connections in the path. So in this case, you might have, this might be a first level switch port going up to a patch panel, then you have a cable going to some cross connect, and then another cable going to the other rack that has the next layer of switching. Again, 300 meters is too long for these AI clusters, but we wanted to stress these and make sure that even under extreme conditions, these expanded beam connections still work well for these applications. All right, so here are 3 results of these extended reach for matched AOCs. Again, the ones that came prepackaged together. The first 5 or 6 data points on these graphs are what were on the previous slide. So from 3 meters to 150 meters. And then we added these extra ones for 200 meters, again, with 4 connections in the path, 250 with 4 connections, and then finally 300 with 6 EBO connections in the path. So as we get to 250, 300 meters, we do see the Q start to decrease. Again, we're seeing a lot of modal dispersion. We're going almost triple the reach that these transceivers are specified for. But we still have some margin. We're still above the Q limit of 5.4 dB. All right, and here are the other 3 of the 6 AOCs we tested. And probably the lowest data point of the day will be this one right here. 300 meters, 6 EBO connections in the path, and we still have about half a dB of margin. Some of these lanes, even at 300 meters, didn't report any errors, which was interesting. They must be very well-tuned lanes there. For the next experiments, we decided to keep the reach to 150 meters, something a little more reasonable for these AI applications, but add a large number of connectors into the path. So we had a bunch of short patch cords, each had an expanded beam connection on the path, and add a bunch of those concatenated together to either add 10 or 20 more expanded beam connections. Just wanted to make sure that these connectors weren't doing anything to the signal, whether the spatial distribution or any return loss problems that we could have. And it turns out we didn't see any problems, whether we had 2, 12, or 22 total expanded beam connections in the path with 150 meters. We still had very good Q values. In fact, it's very small change from one to another because we have short reaches here with these patch cords with the extra connectors on them. And here are the results for the other AOCs. These here, all the lanes reported no errors, even when we have 22 connections in the path and we're going 150 meters plus. So very encouraging. Other thing we looked at was the received power for different number of connections at 150 meters. And we get nice straight lines from 2 to 12 to 22 connections. We see the receive power drop off smooth. There's not much loss, especially when we look at a bunch of these in aggregate. Everything is very well behaved. This is very encouraging results. All right, so in conclusion, we took these 200G SR4 AOCs and we cut them and added expanded beam connectors, and we tested them up to 300 meters. And we also had tests where we had up to 22 connections in the path. Each of the tests that we ran had at least half a dB of Q margin, even at extreme lengths of 300 meters. Now, if we look at more reasonable cases where we have 150 meters and 2 expanded beam connections, and again, this is probably a more than worst case for these AI clusters or applications like that. For those cases, we had at least 7 dB of power margin across all the tests and across all of the AOCs that we tested. And we had more than 1.5 dB of Q margin. So that means that we're well below the forward error correction limit. So any errors that we reported that were recorded with the BER would be corrected by the forward error correction. So end to end, these would be working links with no errors. So in our view, using these expanded beam connections with structured cabling, it's a path to replace or avoid AOCs in your AI clusters. Again, with the benefit of it'll be quicker to deploy. You don't have to clean these connectors because they're expanded beam. And if you upgrade the active equipment in your AI cluster, you can keep the passive cable plant in place, just bring in the new equipment with higher speeds, and the cable plant is ready for the next generation. So these connectors can be very useful for next generation data centers that do anything, any kind of TOR elimination, as well as these AI data centers. So again, thank you for participating in this webinar. Thank you for your attention. Happy to answer any questions that you might have.
Again, thank you, Earl. A very interesting topic. Obviously, the evolution in data centers is happening, and some interesting protocols and topologies going forward. With that, do you see still a some active designs using top of rack structured cabling going forward? Are there still applications for that, or do you see some sort of merge forward?
Yeah, so that's a really interesting question. And I think you'll get different answers depending on who you're talking to. Again, a lot of these large hyperscale and cloud scale data centers, they all do things a little bit differently.
Right.
But I see, in my view, we'll still see applications like this where we have a top of rack switch and we have regular servers, just CPU, not GPU based servers, connected with copper cables and then fiber to the higher level switches. So I think we'll still see that. Some end users talk about a front end network and a back end network. Where the front end's their traditional compute, it's going to look like this on the left, and does their regular services. And then the back end is where they have all these AI clusters that are, I mean, they're not isolated, but they're kind of segregated into their own types of pods and their own architectures. We might see something more like the right. And the architectures come out of the different use cases. So I think we'll see both going forward in data centers.
Yeah, even within the same data centers, you're going to see the sort of a hybrid of combinations of things. That's
Absolutely.
good.
Maybe even in the same room, you have some with
Interesting.
this
Yeah.
architecture and some of the others. So yeah.
Interesting. How large is a 50 micron core expanded to with a lens?
That is a good question. I will need to follow up with my 3M co-authors. I don't want to say a number. It's several times larger. This particular design, I'll need to. So go ahead and send me an email, and I'll follow up on that.
Yeah, and I will be providing Earl's email contact points if you wish to follow up with him, and he can find an answer for you. So are the multimode fibers step index or graded index? Do you think it's possible to replace the expensive glass fibers with high quality plastic fibers, since the distances between the clusters are so small? So that's a good question.
That's a very good question. Yes, yes. So these are graded index, OM4 or OM5 typically. And it is a short reach, but we have to remember that we're looking at very high speeds here. 50 gigabit per second per fiber, 100 gigabit per second per fiber. Next, we're trying to define 200 gigabit per second per fiber. Even for the short reach, to be able to handle that high data rate, you need a good bandwidth from the fiber. And you get that from graded index, you get that from your OM4, your OM5. Plastic fiber probably still won't have the bandwidth to go these kind of distances at these speeds. If we're going at a much lower speed, maybe, but I don't see that happening anytime soon with something other than an OM4 or an OM5 graded index fiber.
Yeah. and an awful lot more data going across those same
Whole lot of data,
fibers.
yes.
At 150 meters and multiple connections, the channel margin looks good, but what impact, if any, was there to latency within that channel?
Yeah, so the connectors themselves don't add any latency, of course, because they're so short and small. So let me pull up so this is the kind of thing we're talking about here. So the only latency from the physical plant would be the length of the fiber itself. So the connections don't add any latency. It's just speed of light isn't infinite, right? It takes so much time to get from one end of the cable to the other. So that's the only source of the latency from what we're looking at here. So again, most AI clusters, people are looking at 100 meters for latency. So the extra 50 meters of the test we're doing here would add some latency, but here we're trying to stress the optical performance, not necessarily looking at latency.
Yep. I will ask the audience again, if you have any questions for Earl, please enter them in the chat. Another question here, the added loss with high numbers of EBO connectors seems low compared to 3M reported insertion loss. Can you try to explain that?
I sure can. I'll go to that slide real quick. So the thing to remember when you're looking at high numbers of connectors, this probably here is where you can kind of get that idea. So when any type of connector, when you specify the loss of the connector, you've got to take into account the distribution that you have in your manufacturing process, right? But when you have multiple connectors in the path, you can add the losses statistically. So this is something like my employer CommScope we do with our, like we have a fire performance calculator. If you have multiple connectors, doesn't matter what type, expanded beam, irregular MPOs and LCs, if you have multiple of those in a path, you don't want to predict their loss by adding the max loss of them all together. So say your max loss for some connector was half a dB, and you have 4 of those, you wouldn't expect the total loss to be 2 dB, 4 times the 0.5. You would look at your distribution, the best practice, look at the distribution, add that up statistically to predict what your loss is here. So these losses, if you're looking at 22 connections, is probably lower than 22 times what 3M might be claiming on a website, because these aren't 22 of the worst in a row, right? What are the odds that we'd have multiple of your extreme losses in a row? Well, that's really low. So if we look at the statistics, this lines up with what we'd expect.
Yeah. Good questions.
Definitely.
I'm not seeing any more questions right at the moment. But again, Earl, that's a testament to how clear your presentation was. Very interesting. Actually, one just came in. Thank you. Why did you perform the test demonstration with AOC cutted in pigtails? Do you suggest to use AOC pigtailed instead of pluggable module? That sounds like a loaded question, but
No, I think that's a fair question. Yeah. Yeah, that was part of it, was just the nature of this test. What was requested from us, or from my co-authors, they were looking at, if we're using AOCs, how does this compare to AOCs? So that's part of it, the specific ask from my co-authors. But in general, you don't have to use pigtailed AOC to use these expanded beam connections. I'm not aware of any transceiver manufacturers right now putting expanded beam connectors on the end face of the transceiver. So you would either need a hybrid cable, or you need a pigtailed transceiver like we essentially made out of these AOCs that have the expanded beam connector. So there's a couple different options, and really you got to look at what's best for your specific application, whether you have transceivers with MPOs and you have an MPO to expanded beam hybrid cable, or if you get pigtailed transceivers that have an expanded beam connector on the end. So those are all options depends on what your sourcing requirements are and how you're installing these. So there's a lot to go into what's best. But for this case, we had a specific ask from our specific co-authors that's why we did it this way.
Good. Looks like one last question. EB connectors don't need cleaning. Is it only because of the expanded beam, or do other factors come into play? For example, fundamental protective design or packaging?
Yeah, so the main thing is the expanded beam, right? If you look at your 50 micron core coming out of the fiber, one piece of dust can block a lot of that. The expanded beam, it's going to block a smaller percentage of it. But the way these connectors are designed, you see the ferrule is right there in the middle. We've got this kind of protective housing around it. These also had anti-reflection coatings. So even if you had something causing a gap, you wouldn't have bad return loss like we see with PC multimode MPO sometimes, where we lose physical contact. So I'd say there's a number of factors. I think the expanded beam is the biggest though, but having the protective housing, having the AR coating, all those contribute to you get good performance even if you don't clean these.
Right. Well, very good. We appreciate a few very well placed compliments, Earl, on your presentation. So
Thank you.
again, we thank you. I'd like to share now the contact points for Earl. Hopefully you can see that the transition here. There we go. Earl, I think, can you see that? Did I transition correctly here?
Looks good.
All right, good. So Earl can be contacted, his email address, should you wish to contact him offline and further the conversation. Each of these IWCS webinar presentation events are recorded, as I mentioned earlier, and will be archived on the IWCS.org website. So you can go back and review the presentation, as well as you can find his written paper on our website from the last event. Normally takes up to a week or two to have these webinars recordings posted. The IWCS webinar will conduct technical paper presentations each month. We also do some sponsored company events throughout the year. So our next scheduled technical paper presentation webinar event will be on Friday, February the 16th at 10:30 a.m. Eastern USA. Each of you will be receiving an announcement for that event. So please feel free to share those announcements with your colleagues so that they can join in and register as well. Excuse me. It's important that we all recognize and thank our IWCS partner sponsors, including CommScope, not only for their content contributions, but also they contribute greatly financially as well to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and trends to you and our global community. So again, thank you to CommScope and our other leading suppliers in our industry for your support. We have some exciting events coming up this year, and of course we want to remind you of our in-person conference in Providence, Rhode Island this October. We're well underway to create a really high-level program and presentations. We also are already 75% booked on the supplier exhibition. So we're getting a lot of strong initial support for the conference. Most importantly, we're looking for your contribution individually and your company to submit an abstract. The technical paper abstract submittal process is open. You can easily submit your one-page abstract for consideration in the conference. Again, very simple process. There's a template abstract for you to look at the format. And we're asking that you kindly submit those abstracts before Friday, April the 5th. Again, that's the most important part of our conference is your work and promoting the efforts that you're doing on behalf of our industry and to promote the leadership of your own company. So please take the time to submit an abstract. And again, for over 72 years now, IWCS and the Cable and Connectivity Industry Forum has been the recognized leader in showcasing the new technologies in cable and connectivity products, the processes, the applications. And again, our next conference will be on October 14th through the 17th. That's Monday through Thursday at the Rhode Island Convention Center in Providence, Rhode Island, USA. So watch your inbox, the social media, and of course our website to learn more as the exciting information becomes available. So thank you for participating today. Again, Happy New Year to you and your family. We hope it's healthy and enjoyable and fun year ahead. We certainly look forward to some exciting events and trends and innovations within our Cable and Connectivity Industry Forum. So have a great weekend and please join us again. Take care. Thanks, Earl.